back to Science Fantastic with Professor Michio Kaku. On Science Fantastic, every week we profile some of the most amazing developments in science and technology, discoveries in science that touch your life and expand the way you view life and the universe around you. And today we're very delighted once again to have a Nobel Prize winner on the airwaves, Professor Frank Wilczek of MIT. He's just written a delightful new book called Fundamentals, 10 Keys to Reality. So maybe you'll have some insight into the world of physics, and maybe some of the young minds out there, maybe you may be inspired to win the Nobel Prize in Physics as well. With us today is Frank Wilczek, MIT professor, winner of the 2004 Nobel Prize in Physics, author of a new book, Fundamentals, 10 Keys to Reality. So, Frank, let me ask you a question. When you were a young kid now, think back years ago, what inspired you to go into science and then into physics?
Well, I had a natural predilection, which I don't really know how to explain, for dealing with numbers, and sort of it's also spurred my imagination to think about really big things. So there was certainly a natural inclination. But I also grew up during a very special time in the history of the United States. It was the Cold War. So science was at a tremendous premium. It was felt to be necessary for the future of the country, the defense of the country. Although it was before my time, their memories were still fresh of the atomic bomb, and scientists were thought of as kind of magicians, and this was in the culture and that all around us. So I got an impression of this was the thing to be was a scientist, and I went to New York City public schools, got all those things reinforced, got in a very, very nice education. And my parents were the children of immigrants, so they were striving. They were very much interested in seeing me do better. And, yeah, all that came together. Now, I didn't really choose to go into physics for quite a while. I was very interested in philosophical questions, mathematical logic, astronomy, how mind emerges from matter. I was also brought up in contact with Roman Catholic traditions, which, although my family wasn't particularly religious, I somehow took it very, very seriously and got the idea that the world had hidden meaning that one was supposed to figure out, and that there was such a thing as cosmic history. And so I had all these incoherent notions. And when I went to the University of Chicago, intending to study how mind emerges from matter, I discovered that I didn't really like laboratory work, and that the study of mind emerging from matter wasn't ready for mathematical treatment. So I kept my options open and went to graduate school at Princeton in mathematics. But when I got there, I found that there were remarkable opportunities to use mathematics and physics, and the rest is history.
Okay, well, I asked Steve Weinberg, Nobel Prize winner, the same question, and he said that for him it was a chemistry kit. When he was a child, he experimented with chemicals and realized that chemicals are made out of other things that are more fundamental than the chemistry that he saw. So, and then I asked Alan Guth, your colleague at MIT, about it, and he said that his parents were not really scientists at all, that he sort of stumbled into it. So here's a question for you. Was there a chemistry kit, a telescope, a visit to the planetarium? For Einstein, it was a gyroscope that stimulated his interest. Was there like one kind of quirky thing that got you steered in the direction of physics and science?
Well, there are many such things. I loved toys when I was a kid, all kinds of mechanical toys. my experience with the chemistry set was kind of unfortunate. It exploded. My parents wouldn't let me continue my career in chemistry.
So you wouldn't get a Nobel Prize in chemistry, just physics. Okay.
Well, this was in the grand tradition of Alfred Nobel, who you may know made his fortune through explosives.
Right.
But I was very interested in mechanical toys. We didn't have a lot of money when I was growing up, but I had a small allowance which I saved up for a long time to get a telescope. So I was always interested in those things. And then, as I said, it was kind of in the air and very much a focus, very much encouraged at school to be interested in technical subjects.
Okay, Frank, you're the author of a number of great books, including A Beautiful Question, Lightness of Being, Fantastic Realities, Longing for the Harmonies. So what about this book? Why did you write Fundamentals, 10 Keys to Reality?
Well, this is a different book. Really, it's meant to be broader in scope and more philosophically and almost theologically oriented, if you could use that word appropriately. It's meant to address the questions that I got from friends and who aren't scientists but want to know what I'm doing and what I've learned from my experience in science. So I wanted to convey the really most important, most essential things that fundamental understanding of the world brings to your perception of the world and your possible experience, and kind of just open people's minds and help them to realize the reality of what that they're immersed in a new way. I call it kind of a process of being born again. When we're babies, we have to construct the world from a kind of confused set of perceptions. Though that world model is enough to get us around very, very nicely and to survive in everyday life, but it's not the world model that is most accurate that you arrive at after using telescopes and microscopes and accelerometers and magnetometers and spectroscopes and all the tools of modern science and logical and critical thinking. And that world is fascinating. It's different, and it expands your mind. And I really wanted to convey that sense that you can experience the world in new ways that are mind-expanding and at the same time accurate, battle-tested, and very real and powerful.
Now, Frank, one of your 10 keys is that there are very few laws. Now, I remember when I was in college, some of my friends were taking a course in English literary criticism, and they would write all these theses about what did James Joyce really mean by this passage anyway. And I began to realize that every year, English literary criticism got more and more obscure and more complicated. But physics became more powerful the simpler it became. That a few fundamental laws could explain an enormous variety of phenomenon, the mysteries of the universe, starting with Isaac Newton. And you mentioned the concept of locality. So explain to us the idea that there are very few laws, and that Newton stumbled on one of them, and he struggled with this question of locality. What is that?
Okay, so that there's a lot to unpack there. So, first of all, the idea that there are very few laws is based on the idea that understanding the world involves two different kinds of processes that have turned out to be fruitful. This has been proved to be a very fruitful approach that really was pioneered by Newton in a sense, that he showed how successful and powerful this could be by example. The two steps are analysis and synthesis. So analysis is the prospect of understanding the simplest units of physical reality, the simplest element of what there is and how it behaves, And boiling things down, it turned out to be possible, to elementary interactions between a few kinds of building blocks. And then there's the opposite process of building back up, of synthesis. That's equally important and to do justice to the world. So we try to find a few basic laws that are as accurate and powerful, and then if we do succeed in doing that, then we have a challenge. And one of the tests of that we have succeeded is that we can start with those laws and build back up to create the world as we actually experience it. Now, Newton found laws of motion a general framework for analyzing how forces affect matter, and one extremely important model law that explained the motion of planets and a lot else about astronomy, his law of gravity, so the law of gravitational attraction. And your audience may know, in any case, I'll just say it, that this is a law you can write down that tells us the force is proportional to the two masses involved and falls off like the distance squared. So a very precise mathematical statement of how gravity works that turned out to unlock many, many phenomena to quantitative explanation. Now, that's a very beautiful law, but Newton wasn't and very successful, but Newton wasn't entirely happy with it because it said that one body acts on another body through empty space with no delay. So there's the faraway planet acts with a gravitational force here immediately, even though there's nothing in between, it's just the two bodies between themselves, and the space in between is kind of just an empty void receptacle. And Newton thought that was crazy. And it was also a very unpopular view. It got him a very unpopular thing. People had struggles with that law. People as powerful minds as Huygens and Descartes had a very different kind of theory that wasn't as precise, but did fill space and sort of had things pushing on nearby things as opposed to acting at a great distance directly. So Newton wanted a theory that would have that character of locality. That is, that the behavior that goes on in the given place in space and time only depends on what's happening in the immediate environment, can be determined in terms of what's happening in the immediate environment. But the laws that he found worked didn't quite have that character. And it was a great development in 19th century physics that emerged in the study of electricity and magnetism that this itch that Newton had, that action should be local, led to a successful theory of how electricity and magnetism works. That there are space-filling fields, we call them electric and magnetic fields, that carry the electric and magnetic forces and you can have waves that travel through space that were predicted out of this local understanding where one point affects what's happening at the nearby point, so you can have disturbances that travel through space as if it were an elastic medium. Or water. Water is another thing that supports waves. That's very familiar. And in the 20th century, that kind of thinking that the laws should be local was extended back to gravity. In Einstein's general theory of relativity, we learned that space itself, space-time, can be bent and can support gravitational disturbances that propagate through space, the so-called gravitational radiation that was just first successfully observed in the last few years. And as far as we know now, this concept that the behavior here and now can be determined entirely in terms of what's happening in our immediate neighborhood is certainly in the fundamental laws of physics as we have it now, and has been a guiding principle to guessing those laws and finding them. So
okay,
that's
Frank,
the principle of locality.
Let me ask you a question about locality. Some people ask the question, if the sun were to disappear right now, this instant, if the sun were to disappear, how long would it take for the Earth to spiral out of its orbit into deep space? Newton would say, of course, instantly. That is, the Earth would instantly fly up into outer space. But then the question is, what would Einstein say about that? Einstein said that nothing can go faster than light. What would Einstein say to the question, what happens if the sun disappears right now?
Well, it's actually inconsistent with the equations to have the sun disappear. There's a conservation of energy or generalization, a conservation of energy momentum that says it's really inconsistent. The equations don't allow you to have the sun suddenly disappear. But what you can do is say, okay, suppose the sun shakes and it does undergo some violent motion, so its mass is getting redistributed in funny ways. How long would it take for us to feel the effect of that here on Earth? And according to general relativity, the disturbance would not be felt immediately, but they would travel out from the sun to the Earth at the speed of light. So if I remember correctly, it takes about 8 minutes to go from the sun to the Earth. So there would be a little bit of delay. We couldn't prepare, though, because it's traveling at exactly the same speed as the speed of light. So by the time we saw it, that something was happening, we would also feel it gravitationally. So.
Okay. Now, Frank, you have a chapter here where you talk about the 4 fundamental forces. Tell us a little bit about how different the nuclear force is from the electromagnetic and gravitational force, and why that eventually led to something called the quark model.
Okay, so we've mentioned Newton and his law of gravity, and we've mentioned briefly developments that really came together in the 19th century to give a theory of electricity and magnetism, a unified theory that now we call electromagnetism. And those forces were discovered by looking at astronomical bodies. In the case of gravity, of course, we also have gravitational effects here on Earth, and it was a great realization to see that those were actually manifestations of the same force. And then electromagnetic forces were originally it was kind of seemed to be kind of epiphenomena that make your hair stand on end in certain circumstances, or you find these funny rocks and magnetite that have funny attractions to each other. But turned out to be a very basic force when studied carefully, and to be when properly understood, the force that really governs the structure of atoms in chemistry, when you put it into the framework of quantum mechanics. So we're summarizing a tremendous amount of physics in a few words there, but there were 2 forces that had beautiful theories going into the 20th century and became very fruitful in combination with quantum mechanics, explaining atoms, chemistry, and molecular physics and astrophysics. Dirac said already in the late 1920s, based on this, that all of chemistry and most of physics was now understood. However, the model of atoms that people used and was based on experimental findings was that you had something called an atomic nucleus, where almost all the mass of the atom and all of its positive electric charge is concentrated, and the atomic nucleus in its size is only about 1/100,000 the radius of the atom as a whole. So it's a very tiny thing, and the forces that held that together were entirely mysterious. And at the beginning, even what it was that it was made out of, that it had ingredients that could be identified, protons and neutrons, and then we'll come to substructure momentarily. But some kind of new force had to be invoked in order to understand what held atomic nuclei together. The gravitational force acting on these tiny scales with tiny amounts of mass is much too weak, and the electric force is actually repulsive because you have a lot of positive charge in a small space, and your thing just really wants to explode.
So, Frank, let's now talk about the nuclear force. You talked about the nucleus at the center of the atom. What's inside the nucleus, and what is inside those particles? Does it go on forever?
Okay, so we needed new force to hold atomic nuclei together. The known forces as of the early 20th century were clearly not enough. So people invented a new force called the strong force to do the job. There's also a weak force, but that's kind of by the by. We'll leave that aside for the moment. It rose to the top of the agenda, I would say, of fundamental physics starting around 1930 to understand what this force was. What is it that holds atomic nuclei together? And there were many, many experiments, many kind of investigations, and it really became quite a mess. People studied the strong force by doing experiments like bashing protons together and at first the idea was that they would push each other in different ways and you could infer what the force was, but that turned out to be much too naive. The protons, when you bash them together, actually produce hordes of other particles, new particles. So the protons themselves it became clear that the protons themselves were complicated objects, and there were many partial insights that led to the idea that you could start to build up a picture of the proton based on its being made out of smaller particles. And skipping decades of development, that is a fascinating story, but involved many thousands, probably hundreds of thousands of PhD years of research and billions of dollars to figure things, to get a hold on this force. The experiments that turned out to be decisive were basically very sophisticated cameras that took snapshots of what's inside protons. Now, ordinary light is not up to the job. It's much too crude. Its wavelength is too long. So it would be like trying to pick up a marble while wearing boxing gloves. People had to invent much more and construct much more exotic instruments in order to take these snapshots. But you could take snapshots of what's inside protons. And when people did that, they found that there were indeed subparticles of two basic kinds called quarks and gluons. And that's the picture that emerged from these experiments. And we got also some notion of what the forces were, but the notion was very peculiar. What emerged from the experiments are that the forces between quarks and gluons, these things inside protons, are very strong. You can't get an individual quark or a gluon out of the proton. So if you try to pull them out, they resist that strongly, and no one has ever been able to isolate a quark or a gluon. But when they were close together, you found the forces got very weak. So this was a very, very paradoxical.
Okay, Frank, we have to take another short commercial break. Once again, you are listening to Science Fantastic with Professor Michio Kaku. Welcome back to Science Fantastic with Professor Michio Kaku. Once again, our special guest today is Nobel laureate Frank Wilczek of MIT. The book that he's just written is called Fundamentals, 10 Keys to Reality. And if you want to know more about Science Fantastic, go to my website, mkaku.org, mkaku.org. Well, where we last left off, we started with Newton talking about the solar system. Then we went down to the world of electricity and magnetism, and then the fields of the nuclear force, including the protons and the neutrons that make up the nucleus. But when you bash them apart, what comes out of the proton are quarks. And then the question is, what holds the quarks together? And this is where Frank's work as a graduate student comes in. So Frank, now tell us a little bit about asymptotic freedom and the work that won the Nobel Prize for you and David Gross.
Yeah.
And
so
when
we left off, we had this very peculiar force that had the character that it gets weaker at short distances, but strengthens when you try to move the particles involved far apart. So that's the kind of behavior you get with a rubber band. If you try to pull things far apart, the force kind of resists, and a rubber band resists large extensions. And the trouble is that although we know about rubber bands, if you try to make rubber bands out of things that obey the basic principles of quantum mechanics and relativity and are not composed of a lot of other things but are very small, so if you try to explain that behavior in a fundamental force, it's very difficult, and in fact was thought to be impossible. But David and I, examined possibilities for using basic principles of quantum mechanics and relativity to build up sort of all the possibilities for behaviors of forces at short distances. And we found out that in almost all cases, the behavior is wrong. That is wrong to explain this experiment. Forces tend to get larger at small distances, not shorter. But we found one kind of theory that was an exceptional case. And so we analyzed that, and it's had very interesting properties. It predicted new kinds of particles called gluons, as well as the quarks that had been observed. And we worked out some of the consequences. And to make a long story, we were led to very specific equations, and we were able to use those equations to make very specific predictions. And that's what ultimately got us the Nobel Prize and led to many important developments in physics.
Okay, now maybe there's some young minds out there that are listening to this radio show, inspired by the idea that even as a grad student, you can do Nobel Prize-winning work. So then, what do you tell them about the next frontiers in physics, like dark matter, dark energy? Is there a Nobel Prize waiting for some young person out there who can figure out what the hell is dark energy and dark matter? What are they?
Yeah, but you better hurry, because certainly in the case of dark matter, because, I think I know what dark matter is. It's something called axions. We have a theory of it that's reasonably precise and tells you it's very hard but not impossible to observe, and people are now on the hunt for it. One thing that I'm doing with colleagues, but there are thousands of people literally doing this around the world, trying to devise the kinds of detectors, telescopes, if you like, or antennas that will detect the axions if they are the dark matter that's all around us. Dark energy is another thing that we seem to need in cosmology. That's not within our present standard model or core theory. it can easily be incorporated, but we don't have a profound understanding of what it is. And there's certainly room for improvement in our understanding there. That really seems to need some new idea to make progress on that one. And sure, it could lead to Nobel Prizes if you have the idea, but that's a big if.
Okay.
So those are great problems, but I think there are other great problems where one can expect progress, and I can confidently recommend to young people, ambitious young people, as things to think about, and where the prospects for doing really important work are great. That includes the realization of ideas about using quantum mechanics to build new kinds of computers. This is called quantum computing, where there are very tantalizing prospects, because quantum mechanics, in theory, can let you do very, very powerful computations, some of which are well beyond what the computers of today can do. But so far, the experimental realization is lagging way behind, and there's room for lots of new ideas, both on the experimental front and also on the front of what we're going to do with all that computing power. Well, we could go on. Do you want me to go on?
Okay. Well, thank you so much for being on Science Fantastic.